Record. All right. So we're going to start with administration again. Our final review starts on this Wednesday. So it's going to be Wednesday, Friday, and the following Monday. What we're going to do with that is each of those days, I'm going to suggest you build a review page to work with on the final, okay? So what that's going to look like is the first one's going to be something like nomenclature. So what are all the rules of nomenclature? Like the first thing you need to remember is which is the highest ranking. So if it has a carboxylic acid on it, that's what we're going to name it. But then we have to go through the longest chain, primary, secondary amines. You're going to build that page, and I'm going to kind of walk you through how to build that page such that it's easy for you to use during the final. Okay. That being said, the final is scheduled for our final period of time during which it was scheduled at the beginning of the semester. For us, I sent out an email on this today. For this class, we have finals on, it will be Friday, May 8th, 11 a.m. to 1:30 p.m., okay? So go ahead and tell your employers or childcare providers that you need to block that amount of time out, and you need to have access to a computer because it will be administered on Sapling, okay? So it'll be multiple choice questions on Sapling, open book, open notes, but these review pages I'm going to teach you about are going to be very, very helpful. And on those review pages, you can add page numbers to get more detailed information, but the overall thing should be on those review sheets. Okay, back to what's due this week for our class. Chapter 14 and 15 videos are already posted. That homework is due on Friday. Chapter 16 videos will be posted today and tomorrow. That homework is due on Monday, May 4th, okay? Your lab is due today at 5 p.m. That's our last lab, and then I'll go ahead and give out those final grades by the end of the week, hopefully. There is a quiz on Friday. It's our last quiz. It's quiz 10. It'll be administered just like before in Dropbox, and if you would contact me ahead of time, you can do try to get that ahead of time or delivered on time as well. And again, those Zoom meetings start on Wednesday. They continue on Friday, and last one is on Monday. Those will be recorded, so you can watch them on the YouTube channel to figure out how to build those pages and to pause and fast forward as you see fit. Okay, so that is our administration for the week. We have a couple different chapters. I'm prepared to give the highlights for chapters 14 and 15 today. And then on Wednesday, I can give highlights for chapter 16. Chapter 16 is polymer chemistry. It's actually my specialty, so I know a lot about that. But I'm going to only want you to know like the basic ideas to help you with your continuing education. Okay. So right now, I will ask if anybody has any specific questions. If not, I'm going to go ahead and hit the highlights of chapter 14 and 15. Okay, go ahead and use the chat there if necessary. Uh-oh, it says my internet connection is unstable. Let me see if I can switch it real quick to something else. Which one do I have? All right, hopefully I'm going to glitch out here temporarily, but I should be able to get on something a little more stable. All right, can everybody see me again? I'm moving. Somebody want to type in the chat? Okay, got a thumbs up there. All right, great. Okay, so we're going to go ahead and move forward with chapter 14 and 15. So chapter 13 was the introduction to carboxylic acids. Chapter 14 is, of course, carboxylic acid derivatives, okay? So the key with these carboxylic acid derivatives is the idea that we can go from a more reactive carboxylic acid derivative to a less reactive carboxylic acid derivative quite easily. And then after we get to a certain point, for example, the least reactive carboxylic acid derivative is the amide. The only way we can do that is we can either dehydrate it and turn it into a nitrile, which we didn't learn in this chapter, or we can hydrolyze it down to a carboxylic acid salt. And that's the only reaction it does. So the key here is looking at these derivatives as a function of most reactive to least reactive. Okay. So in those acid derivatives, we have a couple different kinds, and you can almost think of every, oh, let me start sharing my screen here. Share my screen. Oh, I wonder. Oh, it's there. Okay, good. Share my screen. There we are. Okay, so in all of these carboxylic acid derivatives, what you think of is that, okay, I have a carboxylic acid derivative, which is carbonyl and OH, and every derivative is basically removing water from something and that carboxylic acid to make that derivative, okay? So if we think about going to this acid chloride derivative, I'm gonna use a different color here because I want you to see what I have. I'm going to do here. So this acid chloride is basically the equivalent of taking HCl and our carboxylic acid, removing water. Okay, and that makes a very reactive species. If we just take 2 carboxylic acids and remove water, we get this anhydride, which is also a reactive species. Now, the carboxylic acid is about right here in reactivity. It's a little more reactive than the acid anhydride, a little less than the ester. Then the esters next, where we just took an alcohol and a carboxylic acid. And then the last one is the amide. It's where we took carboxylic acid and an amine and removed water. So if we're looking at reactivity, we want to go from acid chloride to anhydride to carboxylic acid to ester to amide. Okay, and as we learn next, it's all about the idea of what is the better leaving group. Okay, so this is just nomenclature. I'm going to skip over that. You can read that in the book. And so the idea here about reactivity is all about the idea that the leaving group's ability is good or bad, okay? So in the case of these, if we have an acid halide like this, that means chloride ion is our leaving group. Chloride ion is a really good leaving group because it has a very low basicity, okay? Our next leaving group for the acid anhydride would be a carboxylic acid salt. Remember, carboxylic acids are only weak acids, and therefore that makes them a pretty decent leaving group. Then we have an alkoxide, which is even a weaker acid than the carboxylic acid, so it is even more basic. And then our amide is one of the very, very strong bases we have to work with here. So this makes it a poorer leaving group because it has the highest basicity of the set. So if you think about increasing basicity decreases reactivity because it's a worse leaving group. Look at that trend. I think that trend is very important for understanding that reactivity of these carboxylic acid derivatives, okay? So being that a better base is a worse leaving group, that means the weaker the base, the better the leaving group. So our acid chlorides are always more reactive than anhydrides, which are more reactive than esters, which are more reactive than amides. Okay, so that takes us to our second set here. And I want to jump to this last slide first, okay? And the reason I want to jump to this last slide first is because I think it does a great job at kind of drawing attention to the fact that we have the more reactive things can always be cascaded down to the less reactive things. However, I'm going to put my chat back up here. Okay, it's hard to go backwards, okay? So if we look at this, we can take our acid chloride and convert it into the anhydride, the ester, and the amide, and by hydrolyzing in the presence of a base, we can get to the least reactive, which is actually the carboxylic acid salt, okay? The anhydride can be used to create the ester and the amide, but it cannot be used to make the acid chloride here. The ester then can be converted in between itself using the transesterification reaction, or it can be used to create an amide. And once you have an amide, it's really, really, really stable, and so you can't even exchange it with other amines. So the only thing you can do for it is use base to hydrolyze it down to your carboxylic acid salt. Then once you have your carboxylic acid, you use that special reagent, thionyl chloride, to convert it to the acid chloride. Remember, we're not actually up converting from that acid to the carboxylic acid by removing the hydroxide. We actually are converting it into a sulfur compound that makes it a good leaving group. So we're technically creating the sulfonyl ester, which is the reactive species that then eliminates to give us this acid chloride. So we're not up converting our acid, we're actually converting it to a sulfonyl chloride first, which then takes it to the acid chloride. Okay, so this conversion of functionality based on reactivity is the key thing we need to think about when we look at these carboxylic acid derivatives. Okay, which means that when we have alcohols, we can react them with acid chlorides, we can react them with acid and halides, and we can also react them with esters if we want to exchange the esters. So let's look at those reactions. Because this acid halide is most reactive, we lose HCl and get our ester, or in this case, our butanate. Remember, esters have that ANT at the end, okay? Here, when we do an anhydride with the alcohol, we end up yielding one equivalent of carboxylic acid and one equivalent of ester, okay? You always get 1-to-1 because the ethanol will only react with half of the carboxylic acid, and the hydrogen from the ethanol is the hydrogen on the free carboxylic acid. And this is a spontaneous reaction and will go to completion. Okay. With the esters, the ester thing, this is an equilibrium because you have an alcohol exchanging with an alcohol. Typically, this is acid catalyzed. And to drive the reaction to completion, you have to remove preferably the lower molecular weight alcohol, or maybe an alcohol that's not very soluble. So you can drive the reaction by taking it out of the solution, okay? But it still is in equilibrium, so if you add more of the alcohol, it will go back, okay? So this is an equilibrium reaction, so technically we're converting an ester to an ester, but we're kind of tricking the equilibrium to make it exchange. And as we said with conversions here, amides do not react with alcohols under any conditions. You cannot make that happen, okay? So if we look at acid halides, they can react with ammonia, primary or secondary amines to form amides. Notice we have to have 2 equivalents because when we make an acid halide, when it reacts, it forms HCl. One equivalent out of the amine is going to make an HCl salt, and the other equivalent is going to be used to make the amide. So just in like the case with the carboxylic acid anhydride reacting with the ester, with the alcohol, and you get one equivalent of one and one equivalent to the other, we get the same thing here. We have to have 2 equivalents of that amine to neutralize that base. In the anhydride, we do the exact same thing. We have to have 2 equivalents, one to make the amide and one to act as a salt with the carboxylic acid, okay? Now, this always happens, so in both the acid chloride and anhydride, you have to have 2 equivalents, okay? In contrast, if you react an ester with ammonia or a primary or secondary amine, you only need 1 equivalent because the thing that comes off is not acidic, it is just the ethanol, the neutral ethanol that is your leaving product, and therefore it does not form a salt, and therefore you only need the 1 equivalent of the amine to do it. And again, amines do not interexchange with other amines, so there's no reactivity there, okay? So that brings us back to our functional group conversion chart here. So this is how to get all the different groups back and forth, and never touch that carbonyl. You have that carbonyl in all of these functionalities. All you're doing is changing the electronegative atom bonded to that carbonyl. All right. That brings us to our 3rd set of reactions right here, which is the reaction of those groups to form something other than that carbonyl. So we started with this interconversion, and now we're going to do something else to it. Okay. One of the cool reactions here is if you have an ester, you can react it with a Grignard reagent and turn it into other things. Okay. Note, you cannot use the carboxylic acid because Grignard reagents are susceptible to reactions with acidic protons. So if you had the carboxylic acid, it would react with the acidic proton and quench the reaction. The reaction would progress no further. Okay, now Excuse me. Wow, that's really getting worse. So in this case right here, we want to react it with 2 equivalents of the Grignard reagent. The reason is the first Grignard reagent is going to come in and attack a carbonyl, just like we did with an aldehyde and a ketone, okay? But the intermediate there is a carboxylic acid with a hydrogen or with a leaving group next to it. And in this case, we have the alkoxide being able to leave if the electrons on that alcohol come in and kick out that alkoxide. That means we regenerate a carbonyl. When we regenerate the carbonyl, that Grignard wants to react with that new carbonyl. So if we look at this, the mechanism here, first step is to generate this intermediate here. When these electrons right here, oops, when these electrons right here kick in and kick this out, that regains a carbonyl compound, and now we have a ketone, and that ketone will react again. So we have 2 equivalents of that Grignard reaction. It will react twice, and will generate our tertiary alcohol. Okay, once we form that tertiary alcohol, there's no acidic proton or no good leaving group, so it can't kick down again and form a carbonyl again. We now have 3 carbon-carbon bonds where that carbonyl was, and it stops. Okay. So another thing we can do is to, again, react at that carbonyl, okay? Intergroup conversions, we don't react to carbonyl. Here, what we can do is we can add hydrogen across that carbonyl, okay? Now, esters work really well with this because the leaving group turns out to be the alcohol you made the ester from, and you add hydrogens across that carbonyl and give a WELF. And that yields you a primary alcohol. Because you're adding 2 hydrogens to that group, you get a primary alcohol. You have to use lithium aluminum hydride. Things like sodium borohydride, which we used for aldehydes and ketones, will not work. We have to use that lithium aluminum hydride. So you have to be very specific about that when you're reducing down that carbonyl. Okay. So, and this is to draw your attention to the fact that we can reduce the carbonyl with the sodium borohydride, but we can't do the ester. So you can selectively choose one versus the other. Okay. Note, you can also do this with amides too. You can reduce that carbonyl using lithium aluminum hydride. In this case, just like before, whatever the group was on there, you end up leaving the amine on there and you can get a primary, secondary, or tertiary amine. But it's selective. If you started with a primary amide, you end with a primary amine. If you started with a tertiary amide, you end with a tertiary amine. It's very specific. We don't have to worry about additional reactions continuing on. And this is a great example about how you could take the carboxylic acid and do many different things with it. Turn it into an acid chloride, turn it into an ester, turn it into an amide, reduce it down to an alcohol, reduce it down to an amine. So this is a very good way to think about groups being able to move around and choosing your reagent carefully. Okay? So that's the bulk of the chapter 14. Anybody have any questions, go ahead and type it into the group chat here, and I am going to mute myself. Okay. Well, sorry, I forgot to mute myself. I'm allergic to mold, so this is bad. Okay. I don't see any questions in the Zoom chat, so I want to hit chapter 15 real quick. Okay. Now, when we started with aldehydes and ketones, that was starting the introduction to carbonyl, okay? And so that was carbonyls with carbon and hydrogen bonds to it. Then we went to the carboxylic acids, where we looked at electronegative atoms attached to them and showed that there was different reactivity there, okay? Now, with the enolate ions, what we're looking at is using the carbonyl to activate hydrogens nearby to make them more acidic and actually make them do work. Okay, so that's the whole concept here, is that we're not reacting the carbonyl. The carbonyl is activating hydrogens on the adjacent system. So if we look at the carbonyl as our activator here, that means that we're electron withdrawing things away from the 2 carbons next to it. which makes these carbons right next to it susceptible to having a base come in and pull those hydrogens off. The stronger that base, the more likely they are to come off. The stronger or more withdrawing on these, the easier it is to remove that hydrogen. That's why we can make enolates out of this using a strong base, but when we move to something that has 2 carbonyls on it, right here, we can actually use weaker bases because we have 2 carbonyl groups pulling electron density away from it. That means these protons are more acidic than these protons, and that is everything to do with the fact that the carbonyl is pulling electron density from there, okay? So, and again, it has everything to do with the idea that our resonance structure for our carbonyl has a partially positive carbon, and we can use that to our advantage, just like we have an eno-keto tautomerization. We can get this anion to be spread out over 2 carbons and an oxygen, which helps stabilize it, which actually helps make it more acidic. So we went through the entire acidity scale. Again, 2 carbonyls with no electron donating oxygens is the strongest. Now here we have a single ester, so it's decreasing the acidity. 2 esters, decreasing the acidity more. A single carbonyl, and then as we go up to our regular old hydrocarbons, which are less and less and less acidic. So the key here is that carbonyl is the activator, and it's the ones that are right next to that carbonyl carbon that are activated, those hydrogens that are on those carbons. Okay, so we went through the different bases we can use for that. Now, once we form that anion, okay, now it can act as a nucleophile and do all those substitution reactions we learned on ketones. That's all that's happening here. It's just we have to keep track of which carbons are going where, which new bond is formed, okay? So it's the same reaction we have, a nucleophile attacking a carbonyl. Now, then we have to figure out, okay, is it more stable for it to lose a hydrogen and reform the ketone, or is it more stable for it to stay the anion? And that's our next thing that we have to play with. Okay. So the first and simplest reaction is what we call the aldol reaction. That's where we deprotonate a single carbon that is alpha to that carbonyl, and it reacts with another carbonyl of the same type of compound, okay? So notice this is an aldol reaction. It's typically done with aldehydes, so we know exactly which side we're moving the hydrogen on. Notice when we have an aldol here, we only have one set of alpha hydrogens. This hydrogen is not anywhere near as acidic, and therefore we can only remove it from this side, and it's only going to attack the carbonyl. So we have a very specific place where it pulls off and creates the anion, creates that nucleophile, and a very specific place that nucleophile reacts on the other species. So that's why we always generate these beta hydroxy ketone compounds, or I'm sorry, beta hydroxy aldehyde compounds. Notice when we do it with a ketone, we can do it with ketone, it works just fine. It's best to use a symmetrical ketone, or you have multiple products possible, okay? So the key is you're taking away, you're making your nucleophile, you're reacting it on the carbonyl of the same compound, okay? Now, can we do that a little differently? I'm not gonna go through the mechanism. It's pretty straightforward. Can we do that a little differently? Yes. Once we generate that beta alcohol, beta keto alcohol, we can now lose a proton and generate a conjugated system. In this case, we call it the alpha beta unsaturated aldehyde or ketone. Now we have the double bond of the carbon-carbon bond in conjugation with the double bond of that carbonyl. That gives it really cool reactivity because it can react, instead of reacting at this alpha carbon now, we're going to end up reacting at this beta carbon. And we have a special reaction for that. Okay, so can we take the idea of having only one proton we can remove and use it to our advantage? Yes, that's called the cross aldol condensation. That means one of your substrates has alpha hydrogens and their equivalent, and the other substrate has no alpha hydrogen, so only the carbonyl can react. This is what we call a cross-aldol reaction, okay? So we only have one place on the substrate. In this case, it's this acetone here. We can only remove an acidic proton from the acetone, not the aldehyde. And the aldehyde only has one place for it to react because of that. It only has that one carbonyl. So if you can imagine that when you're forming a little bit of this, and as long as you have a lot more of this laying around, it will react with that exclusively, giving you this in high yields, okay? Now, again, we have that beta hydroxy ketone compound right here. Chances are it's probably gonna lose water and give us an unsaturated one as our next step. But the fact is we're using the fact that one of the substrates cannot form the enolate and the other substrate forms one enolate. So that's used to our advantage when we have formaldehyde here, or if we have no alpha hydrogens on that carbon next to the carbonyl, we can use this cross-aldol reaction to our advantage, okay? And we can even make rings out of it, okay? But always, you only make 5 and 6 membered rings. You cannot make bigger or smaller rings, only 5 and 6. But anytime you see that a ketone or a dialdehyde compound that are on the same chain, you might want to think about, oh, can I make a ring close there? Okay. All right, now let's move on to the second set of reactions. Okay, so the aldol is with aldehydes and ketones only, and they must have an alpha hydrogen, okay? When we look at the Claisen reaction, it's a similar reaction, but it has an ester on it, okay? So that's the difference between aldol and Claisen, aldehyde ketone, ester, okay? So in these compounds, if you have a single ester, that means that you have this, wait, okay, let me erase this here. That means that only one side, because this has no alpha hydrogens, that means only this side can be deprotonated, okay? So that means you make the anion here, and then it can only react with this carbonyl, okay? So that's why the Clason's different than the aldol, is we have that ester, we only have one set of alpha protons, and it has to react on that carbonyl to give us our compound here. Most of the time, it gives us what we call our ketoester. So we get our ketone from the addition of our enolate to our ester, and we maintain the ester of one of the compounds, okay? So we have a beta ketoester. So they're one apart, one methylene apart is the beta part, but we always have the ketone and the ester stays intact, okay? So, and it undergoes basically the same mechanism as the other one, and the difference is instead of losing like water in the end of the system, we actually end up losing alcohol. So one of the esters of one of the groups ends up leaving because we're attacking the carbonyl of that one, and that is the alcohol that leaves. The ester on the one you made the enolate on stays the ester, okay? So when we go to the cross-Claisen reaction, where we're looking at only making enolate out of one, whatever you make the enolate out of maintains its ester. Whatever you attacked it with loses its ester and becomes the ketone. Following that bond progression is important. Okay. So, and the mechanism is very similar. We added another step. Note that this was backwards on the previous slides. This is the correct order. The nucleophile attacks one of the esters, giving you this tetrahedral intermediate. And then on the second one, you lose the alkoxide, and then you generate this stabilized beta dicarbonyl compound, okay? So that's one reason the Claisen works really well, is it makes this salt. That salt doesn't react. And so it kind of stays around and waits for you to quench the reaction with a little bit of water. Okay. And so here we go. It stays stabilized, and then we have to quench it with water to make it. Okay. Just like we in the aldol condensation where we can close these, if we have a diester, we can close it again. It's just got a different name. It's called a Dieckmann. And again, it must form a 5 or 6 membered ring. It cannot form 4, it cannot form 7, okay? So we have to figure out, if you have it like this, you'll know exactly how it's gonna close, because it can only form its anion here or here. And so we know that it has to attack one into the other, or this one into that one. But it can only do one or the other, it can't do the same. Okay, but the mechanism is exactly the same, all 4 steps. Deprotonation, attack to form the tetrahedron, elimination of alkoxide, and then acidifying to form our neutral compound. Okay, so just like in the aldol, we can do a cross-Claisen reaction. We still have to have an ester, but we have to have an ester that does not have an alpha hydrogen, okay? So one does have the alpha hydrogen. The one that has the alpha hydrogen keeps its ester. The one that doesn't have the alpha hydrogen is the one that loses the ester to become the ketone, okay? So we'll see that here. Notice that this ester, let me erase again. I'm gonna do it in blue. This ester has no alpha hydrogens, and it loses its ester in the final product. This, it has alpha hydrogens, and it's the one that forms the enolate. It keeps its ester, okay? So it's keeping its ester here. This is losing its ester there, but it still forms that beta keto ester as your final product, okay? Follow the bonds, follow the bonds. Okay. So yeah, we're not gonna worry about this. Oh, yes, this is the one thing that we do have to worry about here, is that once you form this beta keto ester, it's actually pretty stable as is, and so you can actually use this if you want it as your final product. But sometimes you want to use it as a way to build a material that you didn't have before. So you want to build a symmetrical or an unsymmetrical ketone. And in this case, we have a really cool effect. It's the fact that if you clip off the ester and give us the carboxylic acid here, you can use that acid to use heat and a little bit of acid to basically remove CO2 and remove that carboxylic acid group. But the key is it has to be a beta keto ester, because it has to form, if we take this hydrogen away, it has to form this 6-membered intermediate to where it can transfer the proton to here. Let's see, these electrons kick in here, these electrons kick out here. We lose CO2, and we get an enol right here, and then that enol rearranges to the keto form. So, oh, not that one. So, but the key here is you must use your cross-Claisen reaction to generate your ketone. Then you have to hydrolyze your ester and heat it to have the carboxylic acid group leave. Okay. And all the other things on the side, if you have 2 other ketones or other aldehydes there, they're not touched. It has to be only the one that can form the 6-membered ring. So that's kind of cool about that reaction. All right, questions? There are some slides in the book about how you can use these enolates inside of biological systems, but this is going to be covered. If you go do the follow-on course with the biochemistry, this will all be covered in that. And so I wanted to skip ahead and look at the Michael addition, which is another reaction we can do. The cool thing about all these enolate reactions is we're going to do basically the same thing, but in the Michael reaction, we're doing it differently because we typically use a dicarbonyl compound, and we add it to a beta unsaturated carbon. So this is a little different, but we still create an enolate to do it. Okay, so the idea is our enolate creates our nucleophile, but instead of attacking our carbonyl here, because our carbonyl is in conjugation with this carbon here, we have a partially positive charge here and a partially positive charge there. And so instead of having to come all the way in here and attack that, it can attack at this beta carbon. So I think we go into that. Yes, here we go. This is how it works. It must have a double bond. It must be adjacent to the carbonyl. The carbonyl can then, undergo this eno-keto tautomerization. When it does that, we generate our positive charge resonance structure ends up here and here. Okay, so it's back and forth, back and forth. And sterically, this one is a lot more available to being attacked. Okay, and think about the enolates we're using, and back here, it's a fairly big group here, and we're taking charges right in between two large groups. So we want the most sterically unhindered cation that it reacts with. So it's going to react with this one way out here at the end of the chain, so to speak, instead of right here at the carbonyl where we'd have, 4 things coming in with 4 things. And so that's why it attacks at that place. The eno-keto tautomerization, giving us our positive charge out there, and the fact that it's sterically hindered. That's why it works. Okay, so it works best with our diketo species here. Notice we have, this is a diketone, this is a ketone, beta diketo, beta keto ester, this is a beta diester, and it'll even work with some amines, okay? The key here, though, is that you have something big and bulky, so it comes in way over here at the least sterically demanding site. That's why the Michael reaction works. Okay, so it's just the same thing where we deprotonate it, creating a nucleophile. Our nucleophile comes into attack. Then we have an eno-keto tautomerization. It's going to then break down into its more stable form to give us our product here. Now, in the case of a diester or a monoester, you have the option now to do that decarbonylation. So in this one, we've done our Michael addition. We did a hydrolysis of our ester, and then we make that 6-membered intermediate to lose CO2. So we're actually adding two reactions together. But the Michael is the addition of this dicarbonyl compound going to that beta carbon. And then we end up with that is our actual Michael product. And then we can actually continue to do other reactions to give us a different product here. Okay, so if we use nitrogen instead of that enolate, we end up forming some kind of nitrogen, so we end up an amine. Typically, because the amines are nucleophilic enough, you rarely stop at a secondary amine. You typically move to your tertiary amine, but it is it is always going, so the lone pair is acting as the nucleophile and adding to that beta carbon. It doesn't attack the carbonyl, it attacks the beta carbon of the unsaturated system. And we can use that to our advantage for closing some rings, etc. Okay. All right, so those are the highlights of chapter 14 and 15. So chapter 14 is all about interconverting the carboxylic acids and reacting that carbonyl carbon after we've done those conversions. And I'm gonna stop sharing. And then in the enolate chemistry, what we're talking about is not attacking the carbonyl directly. We're actually making an anion adjacent to that carbonyl because of electron trying and using that as our nucleophile. That is our reactive species there. Okay, questions on that? Okay, if you chimed in late, I am going to post this on to the YouTube video. You'll see the highlights of chapters 14 and 15. And on Wednesday, I'll do the highlights of chapter 16, which is polymer chemistry. And then we also will start doing our prep for our final. All right, go ahead and start typing in, or we've got a small group. You can go ahead and unmute and chime in if you wanted to. We only got 6 or so of us here. Okay, so while we break down into individual questions, what I'm going to do is I'm going to stop the recording and let it go ahead and get it ready for uploading. Let me stop